We have got a slim crew tonight. Interesting. I wonder if it's it's meetup fatigue, in that we've got the Fast.AI study group now. We peeled off a EMEA meetup. Maybe all of our North America people, evening people, would rather do it over lunch.
That's okay.
Awesome. Well, so let me, I think it's past the top of the hour. Let me quickly run through this presentation and we can open it up for a nice, intimate discussion. As always, this is our agenda for the session. We will spend the first few minutes with a few announcements that I'll be walking through. The next 10 minutes we'll reserve for community discussion. And then I'll be handing the reins over to David to walk us through the main presentation, which is on the DeepMimic paper. I'm really looking forward to this one. And then I still have this divided up in the main presentation Q&A, but David, you've got the 45 minutes, and generally, you know, folks will ask questions kind of as we go.
That's preferable.
Yeah, yeah. So a few quick announcements. I guess I'll start at the end, just following up on that Q&A topic. David, you'll, feel free to go through your presentation. I'll monitor both the Zoom chat and the Slack and try to keep tabs on questions, and I'll bring them to your attention so you don't have to try to do both of those at the same time, present and monitor for questions. In terms of upcoming meetups, we have got a pretty packed lineup now that we've got this EMEA meetup up and running. So for those who haven't heard about that, we got some complaints from folks in Europe that says, hey, we want to participate live in the meetup, but it's at 2:30 in the morning or 2 o'clock in the morning. What can you do? And so Kai, who participated in the Fast.AI study group, volunteered to lead a more conveniently timed for EMEA meetup, which will be in the beginning of the month. And it's roughly midday for us in the US. I think it's 7 Central European time. And so our next meetup actually the next EMEA meetup is first. I should have put this one first. That's in a couple of weeks. That's on, there's a presenter from Bosch speaking on features in machine learning, specifically their relevancy and their redundancy. And then we've got a speaker that'll be talking about active learning and presenting a paper that I think the paper that he'll be presenting is from NIPS last year, and it was authored by Ksenia, I forget her last name, but she was a guest on the show shortly after NIPS. And then in the EMEA meetup will be the beginning of November, and that'll be focused on trust in machine learning. And that'll be presented by Sharon Glander. If you've kind of been around the podcast on Twitter and even seen my newsletter I shared, Sharon does these great sketch notes of the podcasts. And so she'll be presenting on trust in machine learning. And then Mahesh, who was also a part of the study group, will be presenting on entity embeddings, which is a topic he's very passionate about. And so we've also got a new session of the Fast.AI study group, the deep learning course, and that's running Saturdays at 9. That just started. And so if you've wanted to take that course with us, it's a perfect time to jump in. There are also some folks thinking about running through the Fast.AI machine learning group or machine learning course together. So if you're interested in that, just chime in via the Slack channel. And of course, if you're interested in presenting a paper at the meetup, we've got a meetup CFP link that's right here. You're encouraged to do so. I think our next available slot for both meetups is in January. So you've got plenty of time to prepare. And so next up, community discussion. I am curious what you all have seen of interest recently. But of course, fair game includes the podcasts, industry news events, projects you're working on, et cetera, et cetera. I will start out and just call attention to awesome show came out Monday with Nick Bostrom. Did anyone get a chance to check that one out?
It's very good.
Yeah, I had a great time with that interview and was really, really excited to finally get him on the show. For those who don't know, he is a kind of a leading voice on AI safety and AI ethics. And he wrote a book called Superintelligence that really addresses how we need to prepare for not just AGI, but the inevitable inflection beyond AGI, where artificial intelligence becomes more intelligent than human intelligence. But any conversation on that or any other topic in the next few minutes?
I'm game if nobody else wants to have a go.
Yeah, sure.
Okay, so one of the interesting areas that Nick did not touch on, which I was surprised by, was the idea of augmented intelligence, being that we have a human and an AI essentially collaborating seamlessly.
Mm-hmm.
I've done a little bit of work on this, which you'll see in my presentation briefly, but he was very much of the opinion that AI is distinct from humans and essentially is essentially a third party. It's not part of us or invisible or intrinsic. It's actually quite separate and identifiable. And I was just curious whether you've come across anyone working on a more kind of integrated version of this, where they essentially try and augment human intelligence with artificial intelligence or group intelligence through some form of synthetic something or other. I don't have good words, but it seems to be a topic that's missing in the literature.
Yeah, I think a lot of what folks are working on just in general, I think, the most immediate application will be on augmenting human intelligence. And so, a lot of what we talk about all the time applies there. There is some interesting work happening on like the whole human machine interface. I forget the specific article, but I saw something within the past week or so that was talking about, I think it was talking about how we're apparently very close to players being able to play video games solely using kind of thought control and, some kind of human computer interface. I didn't read the article, I just saw the headline. But, there are definitely people working on that. And we've even seen there was a consumer product that came out a year or two where you you strap on this thing and you can control like levitating these balls or something like that. Does anybody remember seeing that?
Yeah, a friend of mine is doing research in this exact area at Simon Fraser locally, and I'm working with him. I just haven't seen much on the machine learning side. I've seen a lot on the kind of, as you say, the computer-human interface stuff, but not much in the way of using machine learning to augment that. Maybe it's not there. I don't know.
Yeah, I don't know that that I've seen it either. But I would imagine that. It would be interesting to kind of apply machine learning to that, like imaging the brain somehow and using the imaging or whatever signal. Essentially these interfaces are some kind of signal processing application, and so there are potentially interesting ML applications there.
Yeah, and I was just curious whether you hadn't talked to anyone yet who's been covering that material. So.
Not yet, but I'll look for folks.
Okay, cool.
Awesome. Let's see, what time is it? All right, we've got time for another question or topic.
I'd be happy to share real quick, Sam.
Sure.
I've been lately actually building stuff, making some tools for automating data wrangling for applications to machine learning with structured data sets. And I'm actually developing a tool for a new approach for addressing missing values in a data set using machine learning to infill missing values, which I think is a novel approach. And if anyone wants to talk about it, I'm on Twitter at _NICT_.
Was there any particular application that motivated your work on this?
I mean, it was really inspired by the workflow of going through some Kaggle competitions. Okay. And actually that kind of workflow is kind of what inspired the process. But it's meant to kind of automate a lot of the manual data wrangling that goes into those type of address to simplify the process of applying machine learning in a framework of your choice.
And what's the general approach that you're taking with that?
I mean, I'm using the philosophy, keep it simple. It's basically, developing a tool to evaluate each column in the data set and apply an appropriate processing function. And then I think some of the novel approaches are the address of one-hot encoding in an automated fashion, and the use of machine learning models to derive inputs and values.
Interesting.
Yeah.
Are you using Kalman filters or something like that?
Sorry?
Are you using Kalman filters to do the infill? I'm just curious.
I wrote a blog post about it if you want to read more.
Okay, I'll check it out.
Mm-hmm.
Very nice. Yeah, please drop it in the chat.
Oh yeah, I'd be happy to.
Awesome. There were a bunch of other interesting articles that came up this week. There was one from on the Kaggle blog about addressing reproducibility in ML. Google last week published about this what if tool that looked pretty interesting. There was another post about SQL query optimization and applying deep learning to that. I haven't gotten to either of these last few. Bunch of interesting stuff going on. We won't have time to talk about it all this evening because it's time to pass the baton over to David. So I'm going to stop sharing here. David, you could start a screen share and take it away.
Okay, so I think I can present this guy here. There we go at the beginning. Okay, yep, that's good. All right. Do you see my screen?
Yep.
Okay, great. All right, so I'll roll. Here we go. So, hi, I'm David Clement, and I've been involved in computer graphics and data computation for a very long time. It's actually about 40 years now. I started in my early teens, so I've been doing this for a very long time. This particular paper is of keen interest to me because I've been working, and I continue to work, in the interface between virtual characters, real people, and robots. So I'll just walk you through a little bit of my background first, but this is what I'm hoping to cover in the next 30 minutes. So we've got just a quick introduction to me and my background, which I've already started. We're going to cover off on what are character models and animation. I'm going to touch on reinforcement learning and then touch on another very interesting area called phase function networks, which is all precursor work to the DeepMimic paper itself. And in the DeepMimic paper, I have to cover the related work because it's crucial to understand the paper itself. You have to understand some of the work that's done prior to that. I'll then do a quick dive into what the DeepMimic paper talks about, the reward structure that's novel, and the contributions that the paper offers. then there'll be closing comments and Q&A. Okay. So I'm just going to jump right in. So this paper falls in the domain of a large area of research which spans many different disciplines. And the basis of the work is this idea of having realistic agent-based character interaction. So we want to be able to create characters in games that are virtual or real robots or even distant representations of ourselves that allow us to interact with characters in a natural and easy way. So I'm just going to walk you through what's going on here. This is some work I did a few years ago. And what you can see here on the right is an actor wearing a motion capture suit. This is a motion capture studio here in Vancouver. And what you're seeing in these two views in the front here is what the gentleman wearing the VR headset is seeing. And so when I run this video, you'll see that there is a very natural interaction between this virtual character, which is the only thing that the person wearing the headset can perceive, and the real person. So this is kind of like the ground truth that we want to get to with these agent-based systems, all right? We want to be able to produce agents that can interact with us and with their environment in very realistic ways so that we're not constantly saying, oh, that's a robot, or his feet are sticking through the ground, or whatever it might be. All right, so that introduces a whole bunch of different concepts. So this character that you see here in the bottom left is basically a skeleton where the bones are fixed in length, and the only thing varying from frame to frame is the angles that the various different bones have to one another. And then that's mapped onto a mesh, which is the skin. And what we're doing with things like DeepMimic is we're replacing the actor wearing the motion capture suit with a real-time agent, okay? So that's some work I did a while ago. More recent work is this work, and this is a telerobotics application. And what's going on here is that I built this robot here on the right, and there are these two cameras. And I'm operating the robot remotely as if I was inhabiting the robot. There's quite a bit of research on this work. And so I actually take control of the robot using the virtual hand controller. And it would have been great to have an agent to sit between me and the robot to make its motions realistic and more plausible. And that's actually one of the reasons I got involved in the machine learning movement, is that this is actually incredibly difficult work to do without having assistance from something like machine learning. And the simple task of just picking up a ball remotely and dropping it into another container was actually very, very challenging. Okay, but once again, this is exactly the same problem where we have humans interacting with virtual characters or real characters, in this case a robot, and we want to have this kind of smooth, seamless interaction that has very natural physical motion between the two systems. Okay, all right, so, whoops, okay, so now I'm just going to do a very brief introduction to reinforcement learning for those that haven't touched on it. So reinforcement learning is different to supervised learning. In supervised learning, you obviously have the immediate reward and a bunch of images or sound bites or some other reference data set as your training data. And in reinforcement learning, that's not the case. In reinforcement learning, you essentially have an environment and an agent. And so the agent is, in this situation, a machine learning agent, and the environment is a physics simulation. And the way it works is that the agent is past the state of the environment, and then based on its internal model, it then decides and executes a given action. And that action over here on the right then changes the environment. So if I decide to take a step forward, then the environment has changed because my body has moved a step forward. The environment then sends the agent the updated version of the environment. So the new state is passed to the agent. And critically, another piece of information is passed back to the agent, which is a reward. And by reward, I mean a number between 0 and 1, which says that particular action that you took was either good or bad, or none of the above. Now, reinforcement learning is a large area, and two of the authors of this paper, Peter Abil and Sergey Levine, both of whom have been interviewed on Sam's podcast in the past, are clear leaders in this area, and they're out of the Berkeley, Stanford OpenAI camp in San Francisco. So there's quite a bit of theory behind this, and we do actually have to touch on that because one of the key innovations in this paper is actually related to machine learning. So I'm just going to go a little bit deeper. By the way, this is called the Markov decision process, this loop that I'm talking about here. So I'm actually going to try and explain reinforcement learning in terms of this game. Okay, so this is a game called Sequest, which has been mastered by a reinforcement-based system. So let me just explain what's going on here. So there's this submarine, which is you. And when you go to the surface, you fill up with oxygen, okay? But when you're on the surface, you can't actually increase your score. And so the reward for going to the surface is the oxygen, but it's not actually the overall goal of the game. If you just stay on the surface, you won't win. And so the game really is, to get the actual score component, is you have to shoot the fish and rescue the divers and avoid the submarines trying to kill you, okay? And so these are immediate rewards. These are rewards that are occurring in the very near time frame. But there is a more distant reward, which is, or negative reward, which is running out of oxygen, in which case you would die. And so you have to balance these near-term rewards with distant rewards or long-term rewards. And that's the unique capability that reinforcement learning can offer, is that it has the ability to handle what are known as sparse rewards, which rewards, where rewards are actually quite rare. Okay, so just to go into the math just for so here is an experiment I did about 4 months ago in OpenAI Gym, which uses reinforcement learning. So this agent on the floor here is just a physics model of a character. And the only rule I've given it in this particular scenario is try and keep your head as high as you can for as long as you can. So the higher your head, the higher the reward. It's just that simple. And then when you run the simulation, you see that it starts off not having a clue how to achieve the reward. But after 16,000 episodes, it's actually able to bounce and basically sit up. And then as the number climbs higher, it develops these strategies to stay higher longer. So all of this behavior is completely discovered by and being executed by the agent. I didn't teach it to do any of these things. And that really is a remarkable achievement in the remarkable achievement that reinforcement learning offers. So there's a couple of key concepts here. There's something called a trajectory. It's also known as a rollout. It has other names. And really what that is, it's just a sequence of state and action, state and action, state, action, state, action, state, action, state, and so on. So if you consider that you play a computer game, that could be considered a trajectory or a rollout, okay? And the way that you learn the game, which is basically the same way that these agents learn the game, is they start off playing it poorly, they get rewarded for good things, and they get negative rewards for bad things, and they do it again and again and again and again. And so you might have 1 million trajectories or more. And this is where we get into sample efficiency, which I won't be touching on, but it's a very interesting area. So instead of exposing our neural network to images or to structured data like we did in the Fast.AI course, this is very different because what we have is a simulation, or we have the real world in some rare cases, and we're training our agent to navigate through a very complex environment, which may have basically an infinite number of states and an infinite number of actions. And there's another very important concept, which is this idea of what's called the discounted sum of future rewards. So the discounted sum of future rewards simply means that when we take an action, we not only have to consider the next moment in time, the far future as well. But when we consider the far future, we have to essentially bias our actions towards the near term because those are more immediate benefits or rewards over the long term, okay? So in that game I was just showing you, If you have a full oxygen tank, then that is a very distant reward and should be discounted. You don't have to worry about oxygen for quite a while. And more near-term rewards, like shooting the submarines or avoiding the missiles or rescuing the diver, have a higher value in the near term. So there's this concept of discounted sum of future rewards. So down here you can see that when you calculate a reward, you have this discount factor, which is applied at time 0 for the reward at time 0, and then it also considers future times and the rewards offered at those future times. But these future rewards are discounted by this gamma, the concept of this gamma discount variable. All right. So that's all I'm going to go into with reinforcement learning. I can talk more about it if you'd like. I'm going to skip this for now because I'm not sure how far we can get. So there's another novel concept that's used in this paper, which I hadn't seen before, which I'll share with you, which is the idea of a phase function neural network. And what this means is it's very similar to an RNN, where you have essentially a clock which ticks, which is called the phase function. And then as the clock ticks, the weights are essentially switched out for each tick of the clock, or new weights are, you know, blended in using a Gaussian or something like that. So I'm just going to jump to the next slide here. So on the right, you can see a picture of the neural network. And if you look here, there's a dark line. I don't know if you can see that, but it actually repeats. I don't know if you can see my hand, but it actually repeats as the phase goes around. So this isn't one neural network. This is actually a collection of neural networks where each phase, each step in the circle essentially has a separate neural network associated with it. And that allows you to deal with cyclical functions like walking or doing complex maneuvers like side kicks and backflips. And in fact, the DeepMimic paper would not be possible without using these phase function neural networks. So what I'm trying to get at here is the ultimate goal of the paper, because I'm not talking about the whole field right now, the whole domain. I'm specifically focused on the goal of the paper, and there are two goals. So on the left here, you can see that we have an agent that's interacting with the world. It's avoiding the obstacles. Its feet are sticking to the ground, and it's moving in a natural way. Okay, so that is a kind of a generalization of what it is to exist in the world. All of us do these things, and that's what looks natural. On the right, what I'm trying to get at is we want the ability to direct the agent. Even though it's acting in this natural way, if it's just a pre-recorded animation, it's not very interesting. So we want the agent to have the ability to take different paths and make different choices as it needs to. And these are the goals of the paper. All right. So this is the paper, and as you can see, this character, for the very first time that I'm aware of, which is a reinforcement-based learning character, is able to perform very complex maneuvers. So now I'm just going to go briefly into the lead up to this work, because there's been some very, very deep work done in the past in this area. So this particular piece is done by Lidin Louis, who's now at Disney, and Michael Van de Pan, who's out at UBC here in town, and their student, Kang Yin. And this is, I believe, the first time that they were able to train using neural networks, they were able to train a physics simulation to perform complex maneuvers, okay? So that's a key component in the DeepMimic paper, and that was done a while ago. Another key piece of work which was done by Shailen Agrawal is this piece, and I just want to stop and explain what's going on here. The idea is that you have a series of predefined tasks that you want your agent to perform. So make a cup of tea, pick up the box, you know, sit down, these kinds of actions. And then the system has the unique ability to smoothly and realistically blend between these tasks that are essentially finite. So you have a finite state machine, and the agent is able to move very smoothly through the finite state machine in real time. Okay, so this is from 2016. And then 2 landmark papers came out in 2017 at SIGGRAPH, which I had the good fortune to attend. One of them with DeepLoco, and DeepLoco really is the precursor to DeepMimic. It's done by the same people, and I'll let him speak for himself, unless it's too quiet.
It's pretty quiet.
Sorry. Okay. So essentially, what he's saying is that they are using deep neural networks as opposed to past methods in order to train the system to drive an avatar through very complex environments. So the only goal that's being specified here by the operator is the red line, which represents the goal of the agent. The agent is able to smoothly navigate a complex world. It uses what's called a hierarchical learning system. So you have a high-level controller which operates in a long time frame, and a low-level controller which operates in a real-time way. And these are able to drive the simulation. So I won't dwell on that too much. And then the other landmark paper that came out at SIGGRAPH was this one, which was using phase function neural networks to control a character in real time. And to the best of my knowledge, this is the first time that a player is able to navigate a character over arbitrary terrain, and for that character to act in an extremely natural looking way. And this is remarkable work out of the University of Manchester. And really, DeepMimic is the synthesis of the DeepLoco paper, which I just showed you, and this paper. And so these are the precursors to the DeepMimic paper. There is another paper, which unfortunately I couldn't show because it's under copyright by Disney. Lipin Louis has moved to Disney and is doing research there now. And they did some remarkable work, which is similar but different in important ways from this. Okay, on to DeepMimic. So what is DeepMimic? I mean, what are we doing here? So in their own words, DeepMimic receives as input a character model, similar to what I was showing you earlier when I was in virtual reality, a set of kinematic reference motions. So if you can imagine that motion capture actor I showed you earlier performed a series of motions and we recorded those, we can consider those as training data for the agent, all right? And then the final thing, which is why this paper is novel and different from past papers, is this idea of a task. So not only must you very accurately mimic human behavior, but you also have to accomplish a task at the same time. And you have to find a happy balance between looking believable and plausible while achieving the task. So I'm just showing you some examples of this. And so really what DeepMimic is, it is a technique for creating the controller that can drive these characters, okay? So DeepMimic isn't a product, it's not a neural network, it's a technique, all right? It's a way of approaching, taking pre-recorded examples of motion and a character and certain tasks and bringing those together to form a system that can essentially manufacture an agent that can drive these characters in real time. Okay, so that's what the paper is trying to do. So in order to achieve that, it does use reinforcement learning, and it does use all the other components that I was referring to earlier. But I think that it's key that we can dive in and just consider a couple of different things. So the reward then of the system, like the reward I was showing you in the game earlier was don't die, get a high score, rescue divers, shoot bad guys, you know, shoot fish. These make up the reward. In this situation, the reward is made up of 2 parts. The first part is the reward is essentially the smaller the difference between where you are and where I want you to be, the higher the reward. So the agent is rewarded for mimicking the behavior as closely as possible. And that's very interesting and very powerful because it doesn't have to be perfect. As long as you're getting closer, then the system will essentially do its best to mimic the desired behavior. And that's a very powerful idea. So this term on the left here is the imitation objective. The term on the right is the task or the goal objective. So I want you to kick the ball or throw the ball through this target, or, you know, land safely, or whatever it might be. And so this is the directability I was talking about earlier. So this is the generality, behave in a natural way, and then the goal is I want you to achieve this outcome while doing this. So the policy that they're using is very interesting. I just want to touch on this once again.
Hey, David, before you do that, do you have a minute for a couple questions?
No problem at all. Go right ahead.
Nick is asking about, are any of these examples developing their own physics engine, or is the learning primarily for the purpose of developing agents to interact with existing physics engines?
So this particular work was done using Bullet.
Bullet?
A Bullet is a physics engine, an open source physics engine.
Okay.
Very powerful. But I can honestly say that there is no strong connection to a particular physics engine. And one of the examples that they have in the paper is they take the agent and they put it in a different gravity setting. So you can alter the physical characteristics of the environment, the physical parameters of the simulation, and the agents still perform very well. And I will bring up, there is another very interesting physics engine that's available called Majoku. And Majoku is really interesting because it can deal with contacts. So one of the problems in computer games is the idea that you can't, you know, have friction when you roll on the ground and other things. And Majoku really is a novel physics engine in that regard, in that it allows you to have much more accurate simulations. And the simulation I did earlier was actually using the Majoku engine. But there are different frameworks that use different engines. I hope that answers the question.
Yep. And then on the previous slide, you've got the two terms, one of which is the task specific term. How is the task specified?
Excellent question. So the task is specified to the best of my understanding as what is known as a sparse reward. So the agent doesn't receive any reward for approaching the target or for getting ready to go to the target. The only reward the agent would receive is achieving the outcome. And if you watch a supplemental video, there's a section in there where they show how the agent achieves the objective without doing the mimicking. And it's very interesting in that instead of throwing the ball, which was the action that it was told to mimic, it's just, you know, it's told to achieve the objective. And it basically picks up the ball and runs and pushes it through the red ball in order to achieve the objective. Yeah.
Okay. Any other questions for David? All right.
All right, I'll carry on. That's fine. There's not too much more to go, actually. I'm just trying to keep this tight. So this is very interesting. So you were just asking about the goal, and this is exactly what these two terms here is. So these are both fully connected networks. So the 1024 ReLU, this is the ReLU symbol here, is fully connected to a 512 ReLU, which is fully connected to just a standard linear outcome. And the goal is actually fed in here. So if you achieve the objective of the goal, then you receive a strong reward here, and so on. This upper path is very interesting. This is actually what's known as a height map. So if you imagine you're measuring the elevation at every pixel around where the agent or the character is standing, that's exactly what this is. So this is an image. It's the two-dimensional image, but instead of being the color of the ground, it's how high it is. And then this goes through a standard convolutional neural network where you have an 8x8 ReLU layer, it goes into 4x4, and then another 4x4, I believe, is the pooling layer, and then this goes down into the fully connected network as usual. So these policies are actually quite reminiscent of material we covered in the Fast.AI course. So it isn't that exotic. It's not like these things are completely foreign if you've done that course. These are what's driving the agent. So there are three main contributions that the paper has made, and I just wanted to cover each of, well, four actually. The extensive evaluations I can't really cover because it's just the fact that they did an ablation study on this. You can look at the paper for that if you're curious. Reference state initialization is very interesting, and then I'll cover early termination and multi-clip integration. So let's just jump into reference state initialization. So here you can see we have a trained policy, and as you can see, the simulation was able to mimic the training clip with very, very high proficiency. And that's great. But that was actually done years ago in the previous paper I showed you. So that's actually not innovative. Okay. Now, what happens when you don't have reference motion?
Yeah, not bad.
Sorry, you had a question? Sam? Sorry. So when you don't have a reference motion to mimic, the character develops these very weird idiosyncratic behaviors, similar to what I showed you in my experiments earlier, all right? So that's the benefit. Whoops, sorry, that's not what I wanted. I'm gonna go back, sorry. Yeah, so, oh, it's crashed. All right, I have to restart PowerPoint. This is a bug, sorry. I just have to restart PowerPoint. One moment, please. It crashes when that happens.
All right, while we're doing that, if someone had a question, feel free to unmute now. It sounded like background noise, so I did mute it. But if you do have a question, go ahead.
All right. Screen share. PowerPoint. Sorry. PowerPoint, where are you? Okay. Yeah. Sorry, I'm just trying to get back to where we were. Sorry about that. Okay. All right. So I just wanted to play the video and hopefully it won't crash this time. There we go. Okay, good. All right, so we're back on, and that's great. All right, so in this situation, you can see they were able to accurately achieve the backflip. However, if this thing called, without reference state initialization, it actually very accurately mimics what would happen if you asked, you know, a young person to do a backflip without any training, which is, oh, we jumped again. Goodness, one moment, please. I have to be careful here so it doesn't crash again. There we go. All right, so I have to use this control. Yeah, so as you can see, the character kind of lurches backwards, but can't actually achieve the backflip. And no amount of training actually allowed it to do so. And so the key insight here is this idea of what's called reference state initialization. So what they do is imagine that you're standing in front of a huge hedge maze and you're trying to find the answer. You're trying to solve the maze. What they're suggesting is that you just, if you have a solution to the maze, you actually just start them off at different points along the solution to the maze. So in a backflip, you can imagine that you might start halfway through the backflip. So I'll just play for a moment. So you might start at this point, or you might start the simulation at this point. So if you start the teaching at this point, it will learn how to land. And if you start it a little bit beforehand, it will learn how to essentially do different parts of the flip. And this is a key insight that was not known before, I believe. So if you are trying to train a network, specifically a phase function neural network, to achieve a very complex maneuver, you can actually, by training the policy, randomly starting at different points in the reference material, you're able to train it much, much more effectively. In fact, you're able to train it to achieve the goal, which otherwise is impossible, by doing this particular thing. And a visceral example of this to me is this particular thing, which is this young girl here clearly would be at great risk if she tried to do a triple forward roll in a swimming pool without any training. And so in much the same way that you are teaching the agent different aspects of the jump at different times, the coach here is clearly training her how to do these different maneuvers. And this is called curriculum learning. There's another field in deep reinforcement learning called curriculum learning, which I'm not going to go into any depth on. So that's one key finding that they had, this idea that if you're training an agent to mimic a complex behavior, the best way of doing it is to randomly start the episode at different points during the successful simulation, to the successful trajectory. The second innovation is what's called early termination. So what this means is that what's happened here is the character has fallen on the ground already. So early termination is these episodes or trajectories that you go through are very expensive. Physics simulations cannot be multi-threaded, and so these things don't scale well at all. You actually can't use GPUs to accelerate these simulations because the whole idea of a physics engine precludes that kind of mass scale out. So in order to make these trainings efficient, you have to try and have very good sample efficiency. And the second finding they had was not only do you need good sample efficiency, but if you let the simulation run long on essentially bad trajectories, it actually damages the overall training of the network. So what they developed was essentially a set of safety guidelines. You know, if my head hits the ground or if my hand hits the ground, then stop. Don't bother trying to learn anymore. Just end this episode with a negative reward for that last little bit of it and try again. And so that's this idea of early termination. When they introduce early termination, they are actually able to successfully train the agent to do the backflip. Right? Otherwise, they couldn't get it to work. So when you have these two, then you're able to achieve the outcome, which is actually very useful and a really interesting outcome.
Okay. Is part of the idea here that without imitation, it's too hard to specify a reward that causes the agent to do the backflip? Like, we don't know how to specify that, you know, the head needs to be under the body and kind of guide the agent to doing the backflip through the reward function.
Exactly. It's extremely difficult to do it by hand. Like I've hand animated characters for donkey's years, and it's a full-time job. It's extremely time expensive to have a human being sit there and saying, okay, move a little bit, now do this, move a little bit. Oh, it doesn't look realistic, or the physics doesn't work, or yeah, it's a nightmare. And so the ability to use data to drive these animations is huge. Like, it's a massive industry-changing innovation, and the ability to have these agents to be steerable so that you can direct them, and to have them robust so that if there's something in the way, they'll move around it. If there's the stair, they'll put their foot on the stair. This is huge, and because you're training it from natural human behavior, the behavior that the agent exhibits is natural, and that also makes these agents, in terms of robotics, much more comfortable for people to be around. Like, if I'm in a room with a robot that's behaving just like a human, it's not going to set off the same alarm bells as it would as it was going to crashing around, and I couldn't make predictions about its behavior.
Yeah.
So the third breakthrough of the paper was this idea of multi-clip integration, and this has been a holy grail for a long time, and it's actually a very hard problem. So the idea here is that on the left you have these three clips, all right? So you have this clip of the gentleman taking a step forward, the gentleman turning to the right, and the gentleman turning to the left. And as we move through this, you can see the agent on the right is able to smoothly turn corners and interact in a very continuous way. And the way they did this is really interesting, is they trained three separate neural networks. They trained one to smoothly turn right, they trained one to smoothly turn left, and they trained a third neural network to take a step forward. And then they essentially blend them at runtime, which I thought was very novel. So there's no actual training in the blending. They just kind of do a simple linear blend, an alpha blend between the different motions. And they're able to achieve very realistic results, which is very cool. Now, this is also useful in something called retargeting. So this is the Atlas robot. And the interesting thing here is this is a physics simulation. So the Atlas robot is a giant beast, right? It weighs 3 times as much as I do. And the fact that they're able to train an agent to mimic human behavior on something that is, from a physics point of view, is nothing like us, like its arms are heavier, its torso is heavier. Because these neural networks are so general, you can actually train these agents to drive these giant heavy robots so they look real. And similarly here, what's going on, and this is a key frame here, is the agent is able to, in real time, retarget its footsteps so that it doesn't fall down the cracks. And that's a really amazing behavior for these things to do. Footstep planning is a huge field all in itself. Michael van der Pan is a real leader in that research area. So this is another very key innovation which I have not seen before, which is they're not actually even using reference data now. So what they've got is they've had somebody hand animate a T-Rex and a lion in a conventional way, and then they're able to train a neural network to essentially bring those pre-recorded static motions to life and to essentially breathe life into these agents. And they look very much like a T-Rex or a lion, which is, once again, quite remarkable. Okay. So that was multi-clip integration. All right, so I'm basically done my first pass. So really the main contributions that this paper offers very quickly is reference data initialization. So that's the key concept here is that if you are training your network to mimic something, anything, then you should train your network by starting at different points throughout the thing that you're trying to mimic. Okay, this is a key insight that the paper offers. Secondly, if your deep learning algorithm has reached a point of no return where essentially it's failed in its outcome, there's no point in continuing. You should stop that particular trajectory right away and focus your resources on other trajectories that may yield better results. And thirdly, if you do train neural networks to mimic some pre-recorded something or other, whatever it might be, human motion, or it could be anything. It could be a valve opening and shutting. If you've trained your neural network to do that, and a variety of other motions, you can actually just, through simple linear interpolation, blend the outcomes of these different trained networks to produce very good results. The final thing, which I can't share with you, is they did a lot of work on this. I would highly recommend that you watch the supplemental videos. I pasted them all into the TWiML Meetup channel. And I'm available for questions and answers.
Awesome. That was great, David. Thank you. What questions do you have for David?
None?
While we're, is it surprising to you that the simple linear interpolation of the models, you know, the left turn, right turn, and straightforward works? It seems like that seems counterintuitive to me that that just blending them like that would actually produce a result that works. And is there some kind of intuition around that?
It is counterintuitive, and it's not general purpose. Okay, this is very early work, so you'll see future work in this particular direction. So you can't go halfway through a backflip and turn it into a hop. Like it doesn't mean anything. So,
right.
So that I would speculate, if I was going to do the research, I would look for, similar to the idea, the second idea, which is this early termination idea. There is essentially a point of no return. So if you have two behaviors that you're linearly interpolating between, there comes a point where it stops working, right? It just doesn't work anymore. And being able to detect that threshold and essentially to use different strategies as you approach that threshold, I think would be where we will see research in the coming year.
Yeah, I think that's it. It seems like there's, maybe what that's trying to do is to, if you think about it like from an animation perspective, kind of blend, you know, early keyframes in an action, but at some point you have to kind of commit to a direction and do that thing, I would think.
Right, and determining that threshold as you approach it and making a good choice as to which way to go at that point, I think we will see as an area of upcoming research. I would strongly, I would bet money on it. Go ahead.
Yeah, quick question. You know, let me know if I'm misrepresenting. You know, just this is based on the presentation, but it seemed like the mimicking was intended for an agent of comparable composition as, you know, either an animation or a human actor on a video camera. You know, does this technique extend to dissimilar agents from the behavior that it's trying to mimic? I mean, just hypothetical, let's say you have a robot claw, you know, on an axis and you have a human picking up a ball. Does this type of mimic learning?
It does, yeah. So this particular area you're talking about is what's called retargeting. And essentially what happens is, in the simplest case, is you try and correlate a joint in the foreign system, in my case it was the robot, to a joint in the human system. Okay, so I mean, when I built that little robot way back at the beginning, I can go back to it if you like. So this little robot I built, so it does not have all of the capabilities of a human arm, okay? As you can see, it's only got 1, 2, 3, 4, 5, 6 motors in the arm, 7 if you, 7 here. So it's only got 7 degrees of freedom. And so I had to make choices. I had to say, okay, so this motion I'm going to decompose into these motions, and I will retarget my shoulder position to, you know, these angles. So it is a manual process, and I would love to see some work in that area, which essentially automates the process of retargeting. But and I actually think that this particular paper is leading in that direction, but I don't think it goes quite to that endpoint yet. But it's a good question, yeah. So if you're interested, you can either ping me directly or just look up retargeting.
Awesome. Any other questions for David?
Great.
David,
There's one. Is that Satya?
yeah, Satya, yeah, sorry. Yeah, so David, in terms of applying this, right, the applications of this, I think you talked about maybe, you know, video games and maybe animation. Where is this at in terms of the maturity of this particular space in terms of actual applications, and how soon do you think you will start to see some, you know, products or something like that coming out?
So
or is there much more research still pending?
I believe you will see some work in this area quite soon. I believe there is already a startup. I can't remember the name, but I believe there's already a startup that started working in this direction. It's most likely that this would first show up in feature films where the level of sophistication of the people using the software is very high. This is very distant from being something that your average Joe could use to do something useful. So I would see that it would start off as a special project at something like Weta Workshop. It would make its way into a sophisticated tool like Houdini or Maya or something like that. And then we would see the Facebook version of it show up in some kind of, you know, cool animation that you have in Instagram or something. I don't know. But that's the typical trajectory these technologies have. The movie industry, the game industry, I work very closely with a game studio, and they tend to stick to what is safe and known, because these agents are very hungry for CPU power, and CPU power is a premium in games, so I don't think you'll see much of it in the games community for a while, but certainly in the movie industry and in things like Facebook, where you're basically baking video of some fashion.
Thank you.
You're welcome.
David, Nick asked earlier about physics engines. What's the relationship between the physics engine and the tools like OpenAI Gym and DeepMind's kind of simulation tool?
So OpenAI Gym uses Majoku.
Okay.
and it's tightly coupled to that. A project was started called OpenAI Zoo, I think it is.
Okay.
That uses Bullet, because there was a lot of complaint from the research community that you had to pay for Majoku.
Okay.
Really what we're looking for in the physics engine side is GPU acceleration, which is sadly lacking. The real problem with physics-based simulation right now is it's just that it's single-threaded. It sounds so trivial, but firing up 10,000 Amazon instances to do 10,000 episodes is an expensive proposition. Like, that's really expensive. When you've got a GPU with 2,000, 4,000 cores on it, I'm looking forward to a world where we can run simulations on the GPU. And it's getting there, kind of, but it's just not there yet. But it's a good question. And there are a number of very good physics engines out there, Havoc and the usual suspects. Yeah. But Bullet is a very good one. And if you are interested in working with a physics engine, if you do need high contact stuff, like if you're trying to do friction, like if you're trying to play a game of Jenga where the blocks stick to one another in a realistic way, you have to use something like Majoku. But if you're just doing classical physics style simulation, I would highly recommend Bullet.
Great. All right. Well, David, thanks so much. A great presentation. Appreciate it.
Great.
And thanks, everyone.
If you have any further questions, feel free to just ping me in the Slack channel. I'm more than happy to answer them. All right, thanks.
Great.
Thank you.
Good night, everyone.
All right. Take care.
Good night, Sam.